Hey, Mr. Howard again. We're going to continue our integration discussion and move into u-substitution. You may remember when we started taking derivatives for this course, we start off with mainly three big rules, and that was the power rule, the rule for each of the x, and the rule for the natural log. We also had the quotient rule and the product rule, but those were used with other functions. They weren't functions themselves. So we've already covered the integration rule for these three things: the integral of the power function, the power rule, the exponential, and what the rational function that becomes the natural log. It wasn't until we got to the chain rule of taking derivatives that we could really look at variations here. And really what we're going to do with what we call u-substitution for integration is we're going to reverse the chain rule. So we're going to change these rules up a little bit. So I've got the rules that we know up top and a variation down below. And if you look at them, all we did was change the x to u. Now, I will give you the fact that that doesn't look too groundbreaking. But let's think about what we were talking about when we did the chain rule. We talked about that taking a derivative of x, we treated x just as a variable, okay, a straightforward variable. Whereas when we did the chain rule, we used the letter u to denote an expression or a function. So up here, the top row, these are very straightforward rules. Nothing can be changed in these. The n can have different values, but that's about it. Down here at the bottom, u could stand for anything. It could be another variable, or it could be a function, or another expression. So we really got the same type of rule, except what's the main thing here is u du. Okay, so up here when we had x dx, we kind of thought of the dx as just saying, this is the variable we're working with, x. But if you took the derivative of x, you would get 1, and the change in x is just dx. Down here, anytime we have u, we consider du to be the derivative. So let's kind of see what this means. We've got some steps here, but let's kind of go through a process first. So here's my first example that we're going to go through. So we're going to integrate the quantity x plus 1 squared. So one thing we could do here is we could fold that out. We could say x plus 1 times x plus 1, and that would give us a polynomial, and we could integrate the three parts separately. But what the u-substitution does is it lets us take the part that's a little bit more complicated. So if this was just a variable squared, we'd be okay. But since it's an expression squared, we're going to replace that expression, which is x plus 1, with a variable. So we're going to call x plus 1 u. So in that case, where I've got x plus 1 squared, I'll change that to u squared. Okay. Now it's very important because this first example, it doesn't really get the point across, but if we took the derivative of both sides of this, the derivative of u is du. The derivative of x is dx, and the derivative of 1 is 0. So in this case, du equals dx. If I took the derivative of both sides of this, I would get du equals dx. So I can replace the dx with du. So now it looks like a reverse power rule. So I can integrate that in terms of u, which I'll increase the power, divide by the new power, put a plus c with it. But we didn't start with u, and u was basically a placeholder for something more complicated. So we're going to take whatever we set u equal to and plug it back in. So after applying that reverse power rule and going back to the variable x, we have the quantity of x plus 1 cubed divided by 3 as being the integral and plus c. Okay. This is not the easiest thing in the world to get used to. So here is a second example. I might have more examples that I'm going to go through. But we're going to integrate the quantity of x squared plus 2x plus 4 cubed. So we're going to integrate that quadratic cubed. And it's also times x plus 1. Okay, so very complicated. So even if we cube this thing out over here, which would take us a little bit of time, and then we'd have to multiply by x plus 1, we could turn this into a polynomial, but it would take us a while. But what we're going to do is we're going to let this part inside the parentheses, because if this was just a variable a variable cubed, we could reverse the power rule and be okay. So let's let the part inside the parentheses, the first parentheses here, be u. So that quadratic would be u. So in that case, the derivative of u is always du. But the derivative of x squared plus 2x plus 4, of course the 4 goes to 0 and goes away. X squared is 2x, and 2x is 2. So on the right hand side we'd have 2x plus 2 dx. Now there's different ways you can do this, so different videos or different tutorials will show you something a little bit different. Since I know I've got to replace the dx, I'm going to go ahead and get the dx by itself, so I'll divide by the 2x plus 2. So du over 2x plus 2 on the left hand side equals dx. So if I replace the dx with du over 2x plus 2, basically I can pull a 2 out of the bottom, and I've replaced the quadratic with u, I get u cubed, okay, the quadratic cubed, and then I had du over 2, which is the 1/2 out front, times x plus 1 if I pull that 2 out. Well, that x plus 1 on the bottom canceled out with the x plus 1 on top. So now it's a very easy reverse power rule. Increase the exponent, divide by the new exponent, u to the 4th over 8 plus c, and then I go back to whatever u was originally, which was the quadratic, and plug it in place of u. Okay. If you have problems with that, contact me. I will try and lead you in the right direction. Some of them are a lot easier than others. Let's see what else we got. Here's another one very much like the previous one, so I'm going to go on. Here's one that's actually integrates into a natural log, I believe. So this is a definite integral. It goes from 5 to 4, but it's a rational function of 2x over x squared minus 9. So this looks pretty difficult to kind of comprehend where it comes from. But one thing you got to get used to if you do enough of these is if you see a fraction, x in top, x in bottom, try and look and see if you have a function on the bottom and the derivative on top, or something close to it. Because if that's the case, then you can think of that 1 over x, or that du over u. So if we let the denominator here, which is x squared minus 9, be u, the derivative of that would be 2x. So I got du equals 2x dx. So this 2x dx is exactly what's on top here if you think about the way the fractions are written. So we can replace that with du, and then that takes care of the 2x, but the x squared minus 9 we were calling u. So 1 over u du. That is a straightforward integration into the natural log function. So integrates to natural log of u plus c. We'll replace the u. Now since we've got endpoints, we don't need the plus c because it would cancel out. So natural log of x squared minus 9. And when we plug in the 5 and the 4, they're saying we basically get natural log of 16 over 7, which is approximately 0.83. Okay, take a little bit of time to think about that one. Look at some examples I've got in other places. I think this is my last example. Okay. Integration of x times e to the negative x squared dx. So when trying to integrate e to the x, it becomes e to the x, but that's not just x up there in the exponent place, it's a expression. So if that exponent was just a nice variable like u, would be okay, or at least would be moving in the right direction. So we'll let that exponent be u, so u is negative e to the x squared, u equals negative x squared. So take the derivative of both sides, du equals negative 2x dx, as we've got here. So that negative 2 here doesn't really fit this part over here, so you can do some various means if you like. But what they did here is they saw the x and the dx, and they see this on this side, so let's replace that. So we need to get this negative 2 away, so we divided both sides by negative 2. So this x dx can be replaced with negative 1/2 du. So there's the negative 1/2 du for that, and then e was always there, but we changed the exponent to just u. Well, The negative 1/2 is a coefficient or a constant, so it just stays where it's at. E to the u integrates to e to the u. We'll replace that u back with negative x squared. So we get negative 1/2 e to the negative x squared plus c. Khan Academy will explain these just as well, but I was kind of hoping to show you a little bit about the u substitution in action. So if you got questions, let me know.